Okay, I will start my talk by thanking to Rakesh. So after a long time, I think maybe 10, 15 years after we are meeting, we used to meet in TFR when he was there. After that, probably. Yeah. So, okay, this is the talk which will not be like the usual. All the talks I thought like which are very rigorously on the field theory people are doing. So this will be the talk in the other directions where I'll mostly it will be like in the interface of the particle physics and the cosmology. So I will give the talk in mostly in that storytelling manner, not in the hardcore field theory you will see here. So it is a and then basically it was from the quantum physics from micro to macro, and I think like it is also is kind of fitting in that side. Particle physics is like your microscopy, and then the macro is the cosmology, which is the macroscopy side. So it fits. Now let me start. Uh, the whole plan of this talk is basically I'll give you a brief overview of the talk. I mean, basically the dark matter, and to my friends sitting in the bench back. I mean, the back sides. So not meant for the frontline people who are sitting here. It will be very trivial for them, and they might be seeing for many years. So I will start with something like maybe the part one, which I'll talk about, like some evidences, indirect evidences of the dark matter in astrophysics, and then how to calculate the relics of the dark matter, and then I'll talk about how to detect dark matter in different experiments like direct search experiment, indirect search experiment, and maybe some aspect the collider search experiments. And then finally I'll go to my research, which I am doing, maybe that part two, which is my contribution in these directions, if I have enough time. I hope I have time. Okay, so let me begin my talk. As I said, I'll not go for like mathematics. Most of the time I will see only the pictures. So this is the first cartoon I will introduce here to the subject, what is dark matter. So the dark matter, you might have heard. So the purpose of the dark here is I don't understand. The meaning of the dark meaning is I do not understand. For that the word has been coined here is the dark matter. And so what is basically we do not know what is precisely it is. If you ask me what is dark matter, I also don't know. My answer, simple, humble answer. But we know that from astrophysicists, they say us that the dark matter exists in the universe on a large scale. So maybe the existence of the dark matter has been shown to us on like 50 more larger than the galactic scale, let's say beyond 50 kiloparsec on a scale. So that means kiloparsec means kilo means thousand parsec. Parsec means 3.26 light year. Light year means the light travels in 1 year. So that much distance you can imagine how far the physics has been. They are trying to see on that kind of scale. Okay, so it's a very huge number, really macro. Now, the objective of this talk is like basically to discuss what's going on in this area. And so the pictorial, I'll show that here what is called your this is the dark matter, and which is predicted by the Planck satellite experiment. There is some satellite which is spaced at the international space stations, and then which is revolving around the Earth, and it was taking the data for a long time. And for what it measures is that the temperatures in the CMB sky. So the CMB is basically cosmic microwave backgrounds, and this has been kind of formed after kind of around 200,000 years after the universe began, and that time the photons and the basically charged particle and the photon, they decouples and the hydrogen atom forms. So at that time, so the photons which is traveling to us, and those photons are basically the microwave photons, not the photons which is come from the sun and other stars. Okay. Okay. So let's go that. Now, what are our astrophysics friends tell us that there are dark matter exist in the universe, and let us try to believe the way what they said. The dark matter is basically one of the evidence comes the rotation curve, and the rotation curve is what? So you have, like, let's say you have a lone star there in a galaxy, and then you try to the radial velocity of that star which is revolving around the galaxies. Okay. So in this one typical example here, M33 rotation curve, here what is simple formula that you have mv square by r equal to gma by r. From there you see that the velocity or the rotational velocity vr is supposed to fall like here 1 by r to the power half. But what they observe is that this is almost flat or kind of rising to a large scale, so almost like the up to 50 kiloparsecs. And the question they ask is that why it is not the curve is falling or the data is not going in this direction, why the data is like that. And so to answer that, the simplest answer is that you have to have some kind of unknown matter you put it to fit this data. Okay, and that means this unknown matter on top of this AMR. So you say that there are some kind of dark matter is so that you add some dark matter and then you can fit this plot. This is the one evidence where you are introducing an additional particle or additional masses on top of the visible matter. And this additional masses is basically we are calling one of the simpler, that's why we say that there exists some the dark matter in the astrophysical environment. Okay, since I'm telling the story, so the story of the dark matter is not new, and it is quite old, like 100 years old. And it was some of the one gentleman who is called the Henry Wood. So he was taking some kind of data. He was measuring the rotational velocity of this stars, and he was using the Andromeda nebula. And then in that case, he was finding something like the velocity of the stars is quite too high. And then, so unless you have some kind of unknown matter will be there, the star will be escape, they will simply escape from that. So that means your high speed of the stars cannot be sustained by only non-matters, okay, the visible matters. So therefore, this is kind of, and from there he was calculating kind of the density of the dark matter was introducing that times or invisible matter was calling. So it's something like a 2 GeV per cubic centimeter. And the modern value is roughly around 0.3 to 0.4 GeV per cubic centimeter. And the storage also another to that in the chapters, which kind of the Zwicky, he was also measuring some kinds the same things in case of your coma cluster, and then he was measuring some kind of like you see the mass of the visible part is basically 50 times, sorry, the total mass or the dark in the coma cluster, he is finding like the 50 times the visible mass in order to explain this the rotation curve. So that means all this what they are, this astrophysicist tells us that there exists some kind of unknown matter or dark matter, and to explain the data. Okay, so let's trust them. And in fact, it is, not recently, maybe 20 years before. So this is something called another evidence of the dark matter where people observe the collision of the galaxies in the bullet cluster. It's like the two galaxies pass through each other, and then the dark matter, since the dark matter is assumed to be highly weakly interacting, I will come back to that point. But so far, they are talking about the gravitational interactions only. And so they pass through each other. The blue color region part is basically is called the dark matter part, and the red part, which is the gas, which is stuck because they are the baryonic matter. So this is another evidence along that line why when I tell you somebody like the dark matter exists or not. So this is one of the evidence they say. Okay, another evidence along these directions is coming from the CMB itself. That is like when the CMB tells you like the people who are measuring the temperature and isotropy in the sky. So they found there something like this very fine-tuned curve, like the temperature anisotropy in an angular scale. Like if you measure like the photons coming from the two directions has like 1 degree or 2 degree, 3 degree, all these things are shown here all the way to 90 degree. And what they see is that this kind of the pattern in the temperature anisotropy. Okay, so we know that from the very beginning we heard that there is a 2.7 degree Kelvin the CMB photon temperature, but on top of that there is a fluctuations. Okay, so that is called your delta T. And they see that there are lots of physics has been explored in this part, and people, so certain people who devote their whole career for the along this direction, the CMB. Okay, so what is the message from here is basically there is some kind of you have to, so I mean when the CMB is formed, it is without dark matter, we could not have seen this kind of plot. Okay, so the fitting here is basically there are some data points, and there are the lines which is called the theoretical line. They fit very nicely by taking these 6 parameters. Okay, so 6 parameters yesterday Professor Govindarajan was telling about the Hubble tension. This is one of the parameters that that the CMB people who devote their whole period time lifetime for this CMB physics. So this is also one of the predictions. And on top of that, I'm talking about here, there is called omega dark matter square. So there is another parameter they also use, and that value is comes out to be I mean kind of roughly around 0.12. Okay. Sorry.
Why is this? This is CMB spectrum, no?
Right.
As a function of the angle.
Right.
Not frequency.
Angle or the angular momentum.
So why does dark matter cause a bump like that? There is more dark matter in that angle.
More.
Why CMB
Yeah.
is affected by dark matter.
No, it's not the dark matter. It's the temperature. On the y-axis is the temperature. Fluctuation is the temperature fluctuations, not the dark matter.
As a function of angle.
So okay. So there are lots of physics are there. So basically the story, to cut the story short. So if you think like, so the space time is like because of the presence of the dark matter, you have a space time is curved. Okay, and then so this basically they give you the gravitational potential well into which the potential the baryons or the matter is falling. Okay, so now you have a distributions of like the compression rarefactions. Okay, and then so what is basically the what is into the baryons or the matters which is falling into the gravitational potential well, but the baryons are charged because that time the universe is not fully neutral, and so they are coupled to the photons. So photon has a pressures, radiation pressures. So they are now when their particles are falling into the gravitational potential well, the photon pressure is also they are trying to push them apart. So there is a push-pull kind of effort is going on, and at that time, so that is called the kind of the plasma oscillation or the sound wave. So that means they are come all the way to up to the last scattering surface, and from there the photon is finding the free streaming length is quite large. So this part what is showing here is the plasma oscillation pattern up to the last scattering surface. Okay, so the first peak, which is basically it tells you that or not the first peak, the positions of the peaks tells you that the spatially flat universe. Okay, and see this first peak is roughly around angle is 1 degree or L equal to 200 values, and the second peak tells you that there are the ratio of the odd and even number of the peaks tells you that something like the baryon this is extracted from the ratio, and the third peaks tells you that something like the amount of the dark matter it is predicted like that. So on the way, because if you do not exist the dark matter, so these things will like go down. It will not be third peak will not be equal height of the second peak, so it will be like a damped oscillation, damped harmonic oscillator. But the presence of the dark matter tells you that so it is not the fully damped. So that will be kind of this number extracted. So it is not that the dark matter exists along that direction is no. They are distributed. I mean they are giving kind of creating a potential well for the matter which is falling into that well. And sorry, yes, they are almost like isotropic at that time. And so what is basically the temperature anisotropy you see is that the photon which is coming from the deep of the potential well or the top of the potential well. The photon which is coming from the deep of the potential well, they are having kind of losing their energy more, and therefore they are the cool, I mean the blue points, and then photons which are coming from the top of the potential well, they are basically the relatively red or brown color points. Okay, so that's the way we can trust then that is the existence of the dark matter. Now I'll come back to the microscopic physics. So far we are talking about the macroscopic physics of the dark matter, and as a particle physicist, how will you think, how will you interpret whether how is the dark matter is, or what are the conclusions, what are the message you will take from them? So one message is like, okay, dark matter should be a massive particle because they are gravitationally interacting on a large scale, although we do not see on a small scale because gravitational interaction is very difficult to show up in the small scales. And the second, we have not seen them on the astrophysical environment through any kind of electrical signal or or some kind of color signal. So therefore, there should be electrical neutral and colorless particles. And also, our structures are exist, like we have galaxies, we have clusters, and so the dark matter should be existing today also. Okay, so that's the way we interpret. But we do not know, as I said, going to the microscopic physics, we do not know many things, how it is, whether is the mass, how much is the mass, how what is could be charge apart from the electrical charge, whether it can be hypercharge or not. Apart from the gravity, it has any interactions, how the relic is created.
When you say cosmological time scale, what kind of number are we talking about?
I mean, 14 billion years, I would say.
14 billion.
13.8.
Oh, okay. He said 13.8 plus minus something billion. I mean,
Time scale of the universe.
right, yeah. And so the relic, how the relic is created, whether symmetric or asymmetric component. So there are many unanswered questions which is bothered to the particle physicist. And so that's the way they now will go to the microscopic physics. How will I go for microscopic physics? Because the particle physics is only they can see strong interaction or weak interaction or electromagnetic interactions. So then let's say on top of the gravitational interaction, you assume that this particle might have some weak interaction. So let's say this is kind of assumption you have to take. Okay, because gravitational interaction you cannot prove there here because there is too feeble. You cannot have that much technique. We do not have to prove through gravitational interactions, and also their density is too less in this environment where we are living. So we are basically living on in our cluster, or our solar system is almost like on the disk part of our Milky Way galaxy. Yes. So let's say, as I said, this part is that the microscopic picture I'm going now, and the first exercise to do that is, let's say these particles are some kind of a weak interactions on top of the gravity, so they are there in the early universe, and they thermalize. Okay, so if they are thermalized, like they are also like all other standard model particles like baryons and photons and neutrinos, all sorts of particles. So if they are there, then what will happen is that they will thermalize. And but one thing is that the universe is expanding. So then at some point, they will not find with each other. And so that time the number density will freeze out. So, so that means whatever the number will freeze that point, so that will be able to measure today. And that is what the Planck is getting. So our task will be to do all sorts of exercise to create that much relic what Planck satellite is giving us.
In your previous slide, you have the symmetric, asymmetric. What was it?
Okay.
This one.
These are all particle physics questions. So that means symmetric, asymmetric in the meaning, in the sense that, let's say you consider like the dark matter is a Dirac kind of particles. So then you will have also antiparticles. Okay. Now the question is, whether the present universe we see the dark matter particle, whether it was like a mixture of particle and antiparticle, or it is just like only a particle only. We do not know.
So it's something like baryon as
Baryon asymmetry, exactly. Very right, exactly. So this is a cartoon which shows that the dark matter will be kind of annihilating to only the standard model particles in the early universe, and that's why it is the thermal freeze out happens. And what you can do is that you can also create in the present universe in the collider, like we have like proton, you can think like you can collide them and you can produce like standard dark matter in the. And the same way also you can have you can think like the dark matter exists in these rooms, and then they can hit with the like our detector and scatter, and then you will be able to measure. So that's called direct detections. Yeah. So we already assumes, because unless they have the mass, they cannot have gravitational interaction. This mass, this is everything. We do not know anything about that. So for this kind of process, most of the time we start with 100 GeV. That's most of it's kind of the electric scale. So we think like the mass is like, let's say 1 GeV to 100 GeV, or 1 GeV to 1 TeV, this kind of thing. Okay, so
If it is such a massive particle, even though it is present in this,
yeah, okay, but he was
very, very rare.
right, of course, yes. So this is a simpler exercise here. What you do is that you solve the system, like you assume that this particle exists and thermalize in the early universe, and then at some point they will decouple because the universe is expanding, so they will not find with each other, and then whatever the number freeze, so that will be there. And so what you do is that you simply solve the Boltzmann equations for the number density, and then you see that what should be the cross section for them. That will give you the number which was given by the Planck satellite to us, that 0.120. And in fact, it shows that the cross section has to be roughly around like 10 to the power minus 26 centimeter cube per second. In the centimeter square unit, it will be roughly 10 to the power minus 36 centimeter square. And this is a typical weak interaction cross sections. So if you think like in the particle physics point of view, 10 to the power minus 36 centimeter square roughly, this is in the ballpark in the weak interaction cross section. And so that's why it is called some kind of people, or here I calculated. And so if you analytically solve these equations, this is the simple Boltzmann equations. You can think like our universe is like, early universe is like a spherical symmetric ball, and there are n number of dark matter particles are there. It is a volume V. You can calculate the number density is like your n by V simpler, and then the n is constant. Let's say that is for the time being, you do not say there is no interaction among themselves. There are n number of them, and you think like how to evolve due to the expansion. So it is basically dn by dt. Okay, so let's calculate. So dn by dt equal to, with the time, so it is n into d by dt of 1 by v. V is basically that is spherical symmetry, roughly 1 by rq, and so that will give you something like minus 3, let's say minus 3 by r fourth into n, and so that it will be no, there will be r dot term, right? R dot term has to be there. Therefore, it will be minus 3n by rq. N by rq is basically again the number density, and r is just your r dot by r is the Hubble. So that means if you do not have any interactions, basically you will have a dn by dt plus 3nh equal to 0. That means the number density is reducing over the time due to the Hubble expansion. However, now if you switch on the interactions between them, roughly this equation will be something like minus sigma v, the freeze out cross section times your n square minus n equilibrium square. So that is the equation there. So this equation is basically, there is unknown part which is the cross sections. That cross section we are trying to find out, and that numerically it shows that here. So you can easily calculate, I mean, this is a simpler picture. I mean, one can have, depending on how many number of particles, it will be more complicated picture it can arise. And the answer here we show that roughly analytical approximation, if you take, So then it is simply is only one number exists in this case, the relic density. One is only the cross sections, what I said here, and the rest are the non-number. And you want to that one number will decides like one number on the right hand side. So that is your the Planck observed value, and from there what I was saying that if you calculate the cross sections, that is exactly like order of 10 to the power minus 36 centimeter square. So sometimes we didn't know that how much the cross section should be. We just simply say that this particle thermalized in the early universe, and we discovered that the cross section of that particle is order of 10 to the power minus 36 centimeter, which is a typical weak interaction cross sections.
So what is G star?
Relativistic degrees of freedoms.
G star.
Yeah.
The coupling constant.
No. The relativistic degrees of freedoms, which is 100, like for the number of the relativities. Like in case of the standard model is 106.75. If you count all of them, all the leptons, quarks, gauge bosons, all of them, it comes out to be 106.75. And this XF, so this is the time which is mass by temperature. Usually all particles which decouple roughly around 20 XF. Roughly you can see that this number.
The dark matter is assumed to interact with standard model.
Right. Exactly.
The coupling constant. What is the coupling constant?
That constant, I am saying, so that constant goes into here, the sigma v. So far I didn't bother. So what I calculated is that these equations, I put it as a free parameter, that what you said is that the coupling will go inside this part. The mass, coupling, everything will go here, the particle physics part. So far I didn't bother to, all I need, I am calculating this number, how much I number should be to give me 0.1. And the answer is that one, roughly 10 to the power minus 30. The data. And so that tells me that this is a typical weak interaction process. So that's why people like it's a coincidence, and people call it like a WIMP miracle. Okay, so now I convinced you that my bankbencher friends that there exists dark matter which is given by the astrophysicist tells us, and then also we some way we convinced us that could be particle exist which is a weak interacting nature. And now let us go for let's go for such a particle exist in the standard model or not. And the answer is no, such a particle. This is a rough picture of the standard model. You can find it in the Google, such a picture. And so these are kind of center which are like Higgs and all this kind of three generation of the particle quarks and the leptons. On the right hand side you have the photons, gluons, and then the Z boson, the carriers. And then if you count only the neutrino, which is like a similar kind of the properties I said, the neutral, it could be stable, but only thing is that the relic of this neutrino is quite small, so it cannot be like your dark matter property of the dark matter. So we have to go find out some new particles in the beyond standard model scenarios. Something else we do not know what is that. And so what is the strategy? So the strategy is that I have to have kind of my standard model particle which is well known by now, and I have an unknown sector which is called the dark matter. I have to write down a Lagrangian for the dark matter. But if they are existing also in this room, unless they interact with us, I do not know. So I have to have an interaction between them. So that's the usual strategy. And then you have to, if you write down any theory for that, so you have to make sure that they should satisfy all the existing, or they should create the correct relic density, which is the Planck satellite experiment measures. And also there are lots of effort going on in the terrestrial laboratory. There are also in the Earth-based laboratory, there are direct detection experiment, I tell you later. They also have not found out yet, despite there are lots of effort. So that they have to satisfy. So all constant it has to satisfy. Okay. Now, so on that, so many people are working in that direction. So now you have a zoo of particles. People have described so many particles, and so that's why you are saying what should be the mass. Mass is very unknown, coupling is unknown, everything is unknown. Only relic is known. So there are like few things I noted, but there are list will be go down further. Okay. Okay, let me.
What is FIMP and SIM?
So first one I was saying the weakly interacting massive particle WIMP. So that was what I was saying. And then the feebly interacting massive particle F. Feebly, that means the coupling is further smaller. But there could be a strongly interacting massive particles also. So that is also possible. Okay. Okay. So another name is the axion, so like many people familiar to many people, which is also very weakly interacting. That is that's called as sterile neutrinos, dark matter. And that is called the self-interacting dark matter, another class of dark matter which is used to solve some kind of the CMB problem, lambda CDM problems. There could be asymmetric dark matter, particle and antiparticle, and then somehow only the particle survives and antiparticles disappears like that. Okay, so there are this shows is that there are so many efforts are going on in these directions. There are many places that experiments are going on. So there are three kind of experiment, as I said. One is the direct detection experiment, where you see that, so let's say I fix my a target here, and then I wait until a dark matter will hit it, and I will see a peak of a signal. That's called the direct detection experiment. Because all these evidences I said, these are only far distances that which I cannot imagine. Okay, but we have instruments to do that. But these are called the directs. Like here, I have to wait here until the dark matter will hit me, and then I will pick up a signal. So that's called the direct. And then another is called indirect. You assume that there are exist in the sky, the dark matter exists, and at some point they will annihilate to the standard model particle like neutrino, positrons, or electrons, and then the or some protons. And then I will see that I will measure them. So that's called your indirect detection by assuming that the dark matter exists, which is again not so compelling like dark matter direct detections. And that is also called the collider. As I said, I have certain collider experiments are there, so on and so on. So the proton can collide, and you can produce other standard model particle as well as the dark matter, maybe if you trust. And then you try to pick up certain kind of the signatures. Okay, so I will. So these are the theme for which all these kind of experiments are going on. So one, I will go through the little bit more about the how the direct source detection. So I think like this is kind of a detector, and the dark matter is scattering, and then you pick up a signals. So depending on whether it's a photon will be coming out, or whether the electrons will be scattered, or something like. So depending on your strategy, you set up an experiment where whether it will be a positron will come out, or electron will come out, or the photon will come out, or phonon will come out. So depending on your strategy, so it will give you a signal. And so whole idea is that I'll now spend some time. So how much is how the direct detection experimentalists are giving. So-called is called the master formula for the direct detection experiment. So if I set up a detector here, question is, what is I am going to detect? So it is like the total number of detectors. So I say, let's say that n number of particles are I am going to detect. So then it depends on your three things. One is how long, because these are not very immediate process. You have to wait for years and years. Okay, just like the neutrino experiments. So the time part is most important. Exposure time. How long? Let's say the exposure is 10 years of time. And the next is the flux. I have to also see, because these dark matters are not, it's like the flux, how many number of the dark matter exist in our nearby place. And then also what should be the large effective area of cross sections of the detectors. So these are the three important factors which decides how to detect dark matter at the direct source experiments. But the experimentalists do not measure like directly the n. What they measure is that how many number of particles or the events in a particular energy bin. So like let's say 2 to 3 MeV. You can, let's say you can set up a detector where you say that above 6 keV, all my signals will be larger than 6 keV or 10 keV, some things. And then at a particular energy range, you see how many number of events you are seeing. That's the way it's called your dn by d. So how many number of particles you are detecting at a particular energy bin. And on the right hand side, so this particularly it's like the d sigma by d at the cross sections, the effective area of cross sections. So that's the d sigma by d here. And the same, everything is the same. It's like all other particle is independent of the energy, and that's why d sigma by dr. Now, one more thing is the velocity. So the particle's velocity, the particle which is coming to hit your detector is not only one velocities, okay? It's the distributions of the velocity. So what you do is that instead of the v, you insert like a distribution functions, and that is the fv dv, and the integrate and divided by that factor, which is a normalized, then fv dv equal to 1. So from the denominator it is gone. So you have a distribution functions. And then, as I said, you have a minimum to get a signal in your detector. You should have a minimum threshold. Like, so if you say that my signal I should pick up larger than 10 keV, so that means it has to a minimum velocity has to trigger the signal. So you should keep a something minimum velocity, and then from there, you finally end up with like how many number of events you are expecting. That is, this is given by this. But then another important factor is, because your detector consists of only protons, right? And proton also consists of quarks. So that means a bigger ball consists of smaller balls. So that is what it is like. The effective area of cross section is something is like called your the soft structures. It calls like the particle which is coming. Let's say 100 GeV particle is coming and hitting your protons. So it can go to liquid, see the substructure of your that means it will go penetrate into the your balls, right? So that is what you are kind of the structure factor.
So when trying to detect dark matter particles, and when you're saying they're weakly interacting, and that weak interaction is also not very well understood. What is this detection that you're talking about? How do we for sure say that a dark matter particle is not detected?
Yeah, okay. So let us wait for one slide. I will come back, okay, to answer your questions. That's what I am expecting. That let's say an experimentalist, like he has trust the astrophysicist, saying that there exists dark matter in this room, and he set up this particle physicist set up an experiment, and then he is calculating dn by d. Okay. So as I said, these are some kind of the structure factor here, because these are unknown factor again come into the picture. Each time there are some unknown factor come into the picture. So the first unknown factor I said, the distribution functions, like it is not only one velocity, but it is a kind of a distribution of the velocity. And then the next part is, it is not the particle is also penetrating into your ball, the bigger ball, which is a proton, but now it's so you have another factor or some kind of subtleties like the structure form factor is coming. Okay. So finally, let's say this is what it is the experimentalist calculated, that what he's going to, based on this formula, he's going to set up or detect a dark matter. So here it is like the density and the other factor like the mass, cross sections, etc. And there is a unknown part, the distribution function, which is integrating over the total. But apart from that, when you set up an experiment here, you will also see there are lots of backgrounds, because the same signal will be produced. Whatever the signal you are thinking like to pick up, there will be some other physics will give you the same signal. So that's called your background. Now, so the finally total the experimentalist will have is some theory part plus the background part. So based on your calculations, now this has to be compared with how many number of I will detect. Okay, this is my background work, and now how many number of particle I will detect. Okay, so let's say what are the unknown factors here? As I say, you are asking in this formula. This is part I am integrating. The unknown part is the sigma 0, the cross section of the particle, which is dark matter heating, and another is mass of the dark matter. Rest of the things are known. Okay. So the unknown part, which is now I have to calculate, or basically the two things of this unknown formula, whether it is the cross section, another is the mass of the particle. And Reduced mass. It is there are two body problems. It's a reduced mass. Yeah. Okay. This is what I see the form factor. Yeah, it's a bigger ball consists of small balls, so that's why you want. Okay, so this is the
The profile of where little f is itself also unknown, right? In
there are,
addition
yeah,
to the
there are
mass and sigma naught.
this part. Yeah, so
Sigma naught is
roughly
and m chi are unknowns.
yes.
But also the profile of little f itself.
Yes. That part. Okay, some unknown part is there inside the row, which is roughly we are taking 0.4 GeV per centimeter cube in the environment where we are living. Okay, so that is based on certain profile. That means let's say NFW profile or something. I didn't go into the detail because there are certain profile has to be used to calculate the distribution, and from there this number has been arrived. Now people say that this is kind of the pretty how they are distributed solar systems. Yeah, so it's like n-body simulation. People do who this kind of this Navarro-Frank White people who do the n-body simulations. They say that this is kind of the pretty consistent, this large the number who is reaching like 0.4 GeV per centimeter cube. So therefore I didn't say that, I didn't go into there except that only the unknown part, the mass and the cross sections. So that means now I expect, let's say I from this formula in this room, I want to set up an experiment. I see that there are, if I wait for 10 years, I am expecting that 100 events I am expect from this formula. Okay, because everything known. So for a particular mass, for a particular cross sections, I know I know how many numbers. Now after 10 years, if I do not see anything, so that means I will see that there is a constraint on the mass and the cross sections. Right. So background is gone here. Background is already background calculations we that has to be subtracted, and then you see that is what I'm saying. So everything is added, and then based on that I am just expecting after 10 years, so I'm waiting, and if I am expecting that I supposed to get 100 events, and if I do not get 100 events, that means there is no dark matter for that mass and that cross sections. So that is what these guys are doing. So this experimental, this is let's say one of the core, we will do that, that's experimental line, and they found exactly give a exclusion, so-called the exclusion plot in the cross-section versus mass. Like for a particular mass, a particular cross-section is excluded. They didn't get, they expect that this many number of expected, and if they do not get it, that anything, any cross-section larger than that for that particular mass is excluded. Okay, so that means for any experiment, if you pick up, so anything above for a particular mass, anything above that cross sections. Let's say if I 100 GeV mass, and if this for any point if I take, so any cross section above that it is excluded. So that's why I call the exclusion float. What they have not proved below this region, that's called that's still allowed region. Okay, so I think I'm going. So let us. This is also another set of experiment whose sensitivity is the low mass region. But I, sorry.
Results from experiments that have been running.
Yes. These are experiments from the done. People have done already.
Negative result.
Yeah, negative result. You can think like I didn't find anything, so I give a. Lower part is allowed. Lower part we have not proved it. So what we have proved is above that regions, based on their sensitivity, that means this is excluded.
It also means that we understand the backgrounds quite well.
Okay, so that is also people also ask the question. For example, if you consider like 2012 when Higgs was discovered, people didn't. Lots of things happened during that time, right? So far people have done based on their understanding the background calculations. But if sometimes if you see an event, or then people will look for where are the lots of uncertainty, whether in the F, or it is in the distribution functions, or it is in the row. So many places will be the uncertainties are there. So then they will be bothered about. They will redo all this exercise again. If there will be an event, will be the people will find. So far it is not. Okay.
Was the green band and the light yellow band?
These are certain kind. 1 sigma, 1, yeah, for this one.
The light yellow band.
Let's say the 1 sigma and the 2 sigma. A range, okay. Okay, these are another set of experiment where they are also planning to having their sensitivity. You see that sensitivity is here in the larger mass region, but they are here, they are planning, sorry, they are going to like the lower sensitivity, less than 10 GeV or the regions. And there is also another strategy called indirect source now. So which is again, as I said, the particle, you exist, the dark matter exists in the sky, and they will annihilate to the standard model particles like neutrino, positron, electron, then, and you will pick up those because we know very well understood the cosmic ray. So if you see there and the power law distributions, and if you any deviation you see them, then you believe that okay, probably something is coming from somewhere, and you try to fit.
That is self-interacting.
No, any dark anywhere. So I am only finding the flux of electron or positive. Self-interacting is that the part, the dark among themselves is kind of interaction. I don't bother to see that among themselves. What I see is that I try to see the flux, the electron or positron in the cosmic ray, and I. Yeah. So, yeah, exactly. It is the same Feynman diagram in the various way. Right. Yeah, so let's say I think I will not spend much time. This is some of the formula which is people have the, what is you say that the electron or positron or photon is produced in the center of the galaxies, because that's the expected the place where you expect lots of things will happen, and then they will be percolated, what is the diffused. They will diffuse to us, and we will see at the end the measure them here. Okay, and so this is called the diffusion equations. And so here is basically on the right hand side, the standard, but the left hand side is quite known. And what is the right hand side part is called the source term. So that source term could be anything. So it could be a dark matter, it could be something else. And then here is basically, if you assume that this is a source term like a dark matter, and then you can, this is the way you can calculate the flux. This is a formula for working formula for the flux. Here I will be more or less, one can take this here, the particle physics part is here. What is the, in this formula, let's bother about see how this equation was. This is kind of analytical solutions roughly. People have done the kind of approximate, done the approximate solutions. And this is kind of the particle physics part, and this is for the astrophysics part, and this is part is the flux, the V.
The small f here is the same as the small f on the previous slide?
Here. Yeah, that's the same. Yeah.
It's the solution basically.
Yeah, yes, right. So this is kind of the rough working formula for the to get the to measure or to the electron or positron, whatever you want in the Earth surface. And so okay, this is what some of I was trying to fit, and these are come the data, and this is some here long back. Pamela at that time was giving the fast result. Is very much excited that time. They said that the flux is like this. So you see there is a big bump. This is considered to be the background, and then there are kind of bumps there on top of that, and there are lots of arguments were happening whether really it was an excess or not. But the question is, there are lots of uncertainty in the background itself, whether the background I can push it off or down. And lots of paper has been written at that time. I was order of, let's say, 1,000. So the y-axis is basically positron axis, means like the flux of positron divided by the electron, flux of electron and positrons. So positrons are secondary particles mostly. So you will see that if there is an excess, I mean, it is expected that the positrons should not give a, because these are secondary flux. Okay, they should be very suppressed. But if you see a bump or see a large excess, then you expect that they are coming from, there are some sources are there from where it is coming. Yeah, the question is whether the background, background is, if I move this background to here, then there is no bump, right? So that is what the important, that is one important in the CMB, the cosmic ray is like the background calculations also. But nevertheless, people take it seriously because it is a bump, it is not falling down. So all these things we see in the CMB, the Cosmic rays is the flux is going down, power law. Here it was like increasing. That's why people took it seriously. Okay, this is also another one where you see that the protons, antiproton is also kind of the secondary. You will not see that the proton, because our universe is dominated by the baryons only. So if there are antiprotons by AMS02 experiment, so then one has to also think about this. This is also, these are experimental results. Okay. There is another strategy which is the collider, as I said, and there was a last in May 2014 24. So they give this a big tree, various kind of. Okay, so here it comes out the model dependent. When the dark matter you want to prove in the collider, basically you want to produce. So now they take the help of people like us, where you have a model, and then from that model, based on that, they will give you a kind of constraint or the signal. And this is what they have, like lots of processes they consider, and they give some constraint here. And this is an earlier one, but the new results are, I think here the new results, basically they give it in this plane. So it's like if you go to like 1-200 GeV, so these are the various, these are the direct detection data, and then these are the various processes where they are giving in various models. Okay, so for one model you will have one constant, another model you have another constant, and like that. So people do not take it seriously from the collider, because lots of assumptions then goes into their calculations. But the direct detection kind of is more solid than anything else. Okay, so I think I'm running out of time. Maybe I'll go to my work, what I said. So this is part of the introduction. So if anything useful for my bank manager friends, my last half an hour or 45 minutes I spent already. Okay, so now I go to my work, what is I do. Okay, so before that, basically what I said is the theoretical models of the dark matter. So now we have to whatever I said done. So this basically we'll do the BSM scenarios and do the modelings. So this is what it is. Before I go to the modeling part, I have to see that what are the really existing constants, and then if I have to already constants are exist, then I have to think something more. And one of the strong constraint is coming from the direct detections. If the direct detection is mediated by a Z standard model Z bosons, then the cross section is quite large, and such a cross section is already ruled out by the direct detection. That means for that kind of mass particles, experimentalists never seen, they are already excluded. Okay, so in that sense we have to avoid such kind of things. Nucleons, I mean basically nucleon here. Okay, so that means if I have to construct a new model in the VSN of scenarios, I have to take into account those properties, like that it should not interact with it should not have electromagnetic interaction, it should be a stable particle. Apart from that, the mass is unknown, and then the couplings are unknown.
For the PIM case, you had something like 10 to the power minus 26, right?
Centimeter cube per second. In the cross section is like 10 to the power minus 36 centimeter square. Yeah, here it is 10 to the power minus 36 square. Yes. Right. So people have been worked quite a lot. So there are various kind of the models, kind of freeze out. There are freeze-in models, there are asymmetric dark matter models, minimal dark matter, non-minimal dark matter. There are so many names are there, but I don't want to make you afraid of. So let me go directly what I do, some things. So let's say I assume something, a minimal assumptions. There are lots of vector-like leptons are there. I mean, people in the particle physics assume in the BSM scenarios. People who are familiar with vector-like lepton means they do not introduce any anomalies. So in the standard models, is a chiral theory. So that means the right-handed and the left-handed particle, they are treated separately. Therefore, it is introduced anomalies. But it is fortunately it is anomaly free. So if I have to restore that standard model prediction, and I have to also work on dark matter, so I have to introduce something, a new particles, which are vector-like particles. So vector-like means like Dirac fermion. Or if so, in the simplest case, let's say that if I introduce a singlet fermion, then what I see is that by using a dimension 5 operator, like chi bar chi h degree h divided by a mass scale lambda, what we see is that except that the Higgs pole and all other kind of the parameter space is already ruled out from the, that means from the annihilation. So what you want, you have to have is overproduced, right? You need a large cross sections to produce the correct relic density, but the large cross sections are ruled out by the direct detection cross section. So that means they are going opposite directions. You need large cross section to get the correct relic density, but when you large cross section, those are ruled out by the direct detection. So that means the assumption is wrong. That means a singlet cannot be possible. Okay, that's what it the take home message. What about a doublet? If I take a doublet for, then what is that? There is no free parameter here because the doublet has gauge interactions, like your any other lepton doublet. Here it is like a lepton doublet like this, except that this is, but it will have, so that means it will have some kind of, it will give you the correct relic density around some kind of 1000 GeV. Okay, and the rest of this very relic density is very small.
So when you say doublet, you really mean standard model
SU2 doublet. Yeah, okay. So that is also I should be careful. SU2 doublet. Yeah, SU2 singlet, SU2 doublet, all the, because this I'm bothering about SU2 electric theory. So basically when I say singlet means SU2 singlet. Of course, they do not have any color charge, so this is SU3 singlet also. And also when I talk about SU2 doublet, it's SU3 singlet, but SU2 doublet.
but I'm just making sure this SU2 is the SU2 of
SU2 of electroic theory, our Weinberg-Shalom model. SU2L, but it is a factor like fermion. It has both N0L plus N0R and like that. So that is also, as I said, it's only a 1 point where you can, when you get the correct relic density. Now what I do is that I will mix them up and let's see what kind of, I will get a idea. So what I see is basically here onwards, what I'll do, I will take a mixture of a singlet and the doublet. Okay, what I noticed the problem was, in case of singlet, it was mostly overproduced. You see all this part for a given couple is overproduced, and for a 1 to 1000 GeV, if I consider for a doublet, is underproduced. That the relic is much smaller.
So but if it is so light, then wouldn't you have singlet scattering experiments already? Seems like
That means you will give the constant on the mixing. That's what I'm going to do. Okay. So I'll consider a dark matter which is a mixture of singlet and doublet. Okay, so this is called, I will call like singlet doublet dark matter. And okay, so these are certain papers we have worked out with my friend Subhaditya Bhattacharya at IIT Guwahati and all my students here, and Devashish Bora also there. Okay, so let's go to the what is singlet doublet dark matter. Basically, I have the doublet part, and this is the doublet, and this is the singlet. I have a matrix now, and then due to the, when Higgs gets a vacuum expectation value, there is a mixing between the singlet and doublet. Okay, so I'll diagonalize, so that we'll get the 3 states. One is the charge part, which is n plus minus, Okay, so here. Okay, and then there are the neutral component like your N2 and N1 here. N1, N2, and N plus minus. These are the 3 states. And there is mixing angle something like theta. So mixing angles.
So my question is like, if you introduce a doublet like that, wouldn't you have like other terms which are renormalizable in the standard model, which are also allowed by
It will have all sorts of interaction. It's because SU2 doublet, right?
the most general marginal, renormalizable.
Yes. Everything will have, except that it will be a, okay. So one particular point I didn't tell you is called, I should also look for the stability. Okay. And the stability means like it has to, I have to impose some extra symmetry. And this extra symmetry is basically tells me that there will be a G2 symmetry I am imposing here, so that there will be no decay of these particles. Okay. So that will each time there will be 2 n particles or 2 chi particles, or 1 n 1 chi particle will be interacting at each vortex. So that is called your, that gives you the stability of the particles. Okay, that has certain restriction to them. Apart from that, they are like they will behave like usual SU2. Exactly, extra matter, right? I will show you. I'll show you. No, because yes, the d mu, if you write it down, the d mu, the usual that like the way I write down the electron, you think like a heavy electron. This n minus is just like a heavy electrons, n0 is like a neutrino. You think like that.
Actually, my minor comment on that is not necessarily just renormalize the in effective field theory or have higher dimension operators.
Yeah,
With
but I'm
one
saying
over
that, like, the higher things, at least you can hope that they are suppressed by the higher scale. But the normalization is going to be there.
No, but I think if I understand correctly, he's actually having higher dimensional operators, and that's what is causing the suppression in the interaction. But I will let him.
Okay, I'm not so far bothering about the higher dimension. I'm just taking a renormalizable levels so far. And okay, so pictorially I'll show you now. So what are the free parameters in my theory? These are like the mass of dark matter, m1, and then I say the mass of the doublet, which is like roughly m2, and then there is a mixing between the singlet and doublet. So there are three parameters. So I just like pictorially in the cartoon, I just think like this is the cake, on top of that the cherry, and this cherry is basically the doublet, and cake is my singlet. And I have to quantify how much large is the cherry and how large is the cake. So that's we'll call the mixing. And the cherry part is basically, it has mass m2, and then the cake part is the mass of your m1, the light singlet particles. Okay, so rest I will basically I'll just do some kind of computing, and then I'll give you some constraint on the mixings. And the computation as I have to do, I have to find out, reproduce the correct relic of the dark matters. So that means I have to solve the same equation that I was writing in the very beginning. But now we have not only one particle, I have also one singlet, and there are two the doublet, the dark sector particles are more complicated. So you will have some complicated cross sections. And what we have to solve this equation to get the constraint on this mass and the couplings or the mixings. Okay, so TLC, so here these are the all processes. Okay, so it's basically, it constitutes like all annihilation processes. N1 is going to all standard model particles. This is called the co-annihilation. N1 will be co-annihilating with the partner with N2. It can go to standard model particles. It can also, N1 can also co-annihilate with N minus to all standard model particles. Similarly, N2 N minus can annihilate. That can also give. So there are three particles in the dark sectors, and there are lots of processes going on. So pictorially they are shown here. I think it's not so important. Let's go directly. Here. This mass matrix here is diagonalizing, and the lightest mass eigenstate is N1, and this is the next to lightest particle is like your N2, and then N plus minus is mostly the charged particle, which is the doublet mass. Okay, so we solve this. Here is the result. So the result is basically M1 is basically M dark matter, and then if you solve this Boltzmann equations, and I will give you the result. There are three free parameters are there, M1, M2, and the mixing angles. M2 is basically realized in terms of the delta time. Delta time is M2 minus M1. So in the color code is basically the mass splitting, and the y-axis is the sin theta mixing angle, and the x-axis is the mass of dark matter. And so here it is the results where you will show you, I mean, where it will give the correct relic density. Basically here it says that the correct relic density. And you see the spectrum exists all the way from 1000 to 1000 GeV in various regions. And the sin theta is roughly larger than maybe few times 10 to the power minus 4. Okay, so that is what it is give you in this. If the mixing is like that, you will get the correct relic density. Okay, and the same thing also shown in the other way, like your mass split in delta m versus the mass, and the color code is the mixing angle, and all these regions are like this. So it's basically here is overabundant zone, and here it is underabundant. That means dark matter you will not get enough relics. When the co-annihilation is more, the cross-section, the mass splitting is small, the co-annihilation will be large. And if your coannihilation is large, so the relic will be small. So that is what it is. And in this case, mostly the annihilations. Okay, so that is the exercise. I mean, whatever the question I was asking, I got the answer. And then I also asked another question. What will happen if the mixing is further smaller? Here, I saw that already, I also read, but if I do a further smaller mixing, what will happen? And we asked the question, can we be able to get the correct relic density of the dark matter? And the answer is yes. And the reason is there why the angle has to be larger than 10, few times 10 to the power minus 4. It's because there is one process in this case, Boltzmann equation, which is independent of sine theta. So this particular process which is independent of sine theta. And because of, and we are assuming that in this statement, all of them are decoupling at the same time. And that's why you get the constant. But if you assume now you separately treat, and that's what we have done it here. We have, instead of only one Boltzmann equation, now we have two sets of Boltzmann equations. In one case, how do we do that? We say that first, N1, which is like the dominantly singlet, which is one sector. And then we have, there is a dominantly doublet, which is the sector 2. And there is another called the sector 0, which is like the dominantly standard or mostly standard model particle. So in this way, we divided the three parts, and then we wrote the two Boltzmann equations. One is for the relic of the N1, another is the relic of your N2, and then we add it up. Okay, so most important part is here, this is the terms. Okay, yeah, so these are the two terms which are called your decay plus co-scattering. Co-scattering is meaning is a particle can also co-scatter with a standard model particles. Instead of co-annihilation means like a dark matter particle will co-annihilate with another dark sector particle and it will go to the standard model particle. But co-scattering means a dark matter particle also scatter with the standard model particles and go to another standard model particle in the dark sector particle. So this process also, that part was ignored earlier. And we did it here, and we particularly one sample I showed you. If they will be like the large mixing angle, so they will decouple at the same time. You see, this is the equilibrium number density, and this is the freeze out number density. So one is for your singlet, another is the doublet. So doublet relic is a bit smaller because of the gauge annihilations, and the singlet will be like a dominant component here. And they are decoupling at the same time, same temperature for the large mixing angle. But the mixing angle is small, the singlet will be decoupled very, very early. What it will co-scatter, that means it will co-scatter with the standard model particle and it will come back to the correct relic. However, the doublet will have always gauge interaction, so it doesn't care about that. So therefore, its relic is always smaller. Okay, so I think I will not bore you. I more or less I told you. So I just, whatever I said, it is kind of the proof of that. If I do not take into account of the co-scatterings, so then you see that the effect is basically the same things. But when you take in the co-scattering, without co-scatterings, you will have this one. And if you have a co-scattering, the relic will be smaller. So that means you have additional components, which was ignored earlier. And now we are taking into account. Yeah, I will finish it. And if you take into the effect of the co-scatterings, is basically you will get in these results. And let me go back to this is the final result. When you take into everything, the co-scattering, this is the kind of, earlier, basically, if you compare the earlier data, so there was, this region was there, but this region is underabundant. But now we are getting some new points in this region. And this is another exercise we did it to check the effect of the co-scattering basically by defining a new parameter. And ultimately, we showed that it's kind of all the way to 10 to the power minus 6, we get the correct relic density. Okay, maybe I don't have much time. Here is another thing, like if you further smaller, if you take whether it will possible, and the answer is also yes. And there is another mechanism called the freeze-in mechanism through which you can get the correct relic density also. And so this is some direct. So let's say here, this picture is the take-home message. So now sin theta in the mass plane of the sin theta versus mass of dark matter, where the singlet doublet I will show you. So the large mass in this part is excluded by the direct detection experiment because the mixing is large. As if you remember, very beginning I said the Z-mediated process is ruled out, and therefore when singlet doublet mixing is large, basically it will give you the large direct detection cross section. So therefore it is ruled out. But then if you suppress your singlet doublet mixing, you can get the correct relic density through the annihilation and co-annihilation, the first diagram I showed you. And then if you reduce further, co-scattering can come into the picture and it will give you the correct relic density. And if you reduce further, then you will get overabundant. That means mixing will be small. Now they will not be, any particle will not be annihilated, and then you will get overabundance. And then if you further smaller, again you will get but a new mechanism which is called the Frisian mechanisms. And if you further smaller, they are underproduced. That means if the mixing is small, singlet cannot be produced. And doublet, if the doublet are anyway there, they have gas interaction and their relic is very small. Okay, so this is okay. So maybe I will take 1 minute. This is what is called the how to prove the hypothesis at the collider, and this is one of the mechanism called the displaced vortex signature. If the mixing angle is small, the charge partner of the doublet, it doesn't care about the mixing, right? So it can be produced at the collider, but it can decay to the neutral component. So that means if there is a mass suppression will be there, so you will basically in the small mass regime you will get the large displaced vortex signature. So this is one of the I showed you, where you can get everything satisfied correct relic density and direct detection constants. Okay, probably I do not. I have some papers, but I know I will stop it here, and I will go directly to the last concluding sections. Thank you.
So considering only one parameter, which is
Mixing.
no, relic density is the only thing which you want to make. But
And also, yes, exactly. That's the objective.
there are a lot of other parameters which people want dark matter to produce. For example, core cusp problem, the density in the center, what is the effect of the gravitational waves, all those things.
Yeah. So that model part will come. So which I have some few things I didn't describe here. So papers, all these things. But yeah, that's a generic. I didn't bother to. If there is only dark matter problem, this is I consider a singlet doublet, and this is very nice predictions I showed you. So called the singlet doublet dark matter.
Spin independent interpretation. Why don't they bother most?
Experiment biased us only, because experiment, the way experiment gives you the others of the nucleon, where the experiment is like there are certain experiments, they are also taking into account of the spin dependent cross sections, but mostly the leading experiments are now spin independent cross sections.
Actually take into consideration the polarization of the
Net spin of the nucleon is 0, is basically is averaged over. So there you have a net spin. But those cross sections are very, when the constants are not that much significant or stringent in comparison to that spin independent.
Can you remind me for that only singlet model, the advantage of the singlet? So it was SU2 singlet, you said it was colored singlet, so it has only U1 interaction. Or
No, SU2 singlet, I wrote like dimension 5 operator.
okay.
Chi bar chi.
It doesn't have any human interaction.
So that's why I'm confused, like what interaction it has.
This is the interaction. Yeah, there is no U1.
Yes, that's what I'm confused.
Hypercharge, hyper singlet means hypercharge 0, neutral particle, hypercharge 0. There is